essential elements regarding the eigenvalues and eigenvectors are that any matrix A can have a specific eigenvalue, which can be like lambda 1, lambda 2, etc. Now, each one of the eigenvalues, it constitutes or it makes up another matrix, and this matrix can be associated an eigenspace. So let's assume for a moment that we have A, let's give it 2 by 2. Okay? A matrix 2 by 2, we can have lambda 1 and we can have lambda 2. Now, this lambda 1, it has its eigenspace. And lambda 2, it has also its own eigenspace. And what is the eigenspace? We know what space is, so we know, for example, we have spaces, subspaces, one-dimensional spaces which are described by a single vector. We can have two-dimensional spaces which are composed of as a linear combination of two vectors which are linearly independent. So this is what we know regarding the eigenspaces. So it looks like this eigenspace of lambda 1, it is equivalent to the null space of which matrix? Of the matrix A minus lambda 1I. Okay. So the null space of this new matrix, its dimension will give also the dimension of the eigenspace of lambda 1. So the examples we solved in the previous session, what did we observe? We observed that for two different examples of 2 by 2 matrices, we found that the dimension of the null space, it was always 1, right? So you go back at the previous session's notes or lecture notes, and this is what we are going to observe. Again, we have lambda 2, which is another eigenspace. This has a corresponding eigenspace, and this eigenspace is again the null space of matrix A minus lambda 2 times R. Okay? Again, they will, so in the previous example, for whatever we are not here is yet, this was, for example, one of the vectors which defines the one-dimensional eigenspace of an eigenvalue equal to 2. Okay, so if you check the notes of previous hour, this 2, this was the eigenvector, and this one, this was the corresponding eigenvector. The dimension of both of these respective eigenspaces, they were 1 and 1. Now, another thing that we can add, let's assume we have a couple of concepts which are very essential, which is the algebraic multiplicity. Algebraic multiplicity. Regarding the algebraic multiplicity, we can write this one as Am. Okay? The algebraic multiplicity, what it stands for, so if we have, let's give the definition here. If lambda I is an eigenvalue, if lambda I, it is eigenvalue, and lambda minus lambda I to the power k is the highest power, so it is the highest, let me call this one, is a factor in the Pn lambda. Then this implies that the algebraic multiplicity of lambda I is equal to k. Okay, so this is what we mean with algebraic multiplicity. In the examples we solved in the previous session, the algebraic multiplicity of all of the lambdas was equal to 1. Why? Because we had expressions like this, lambda minus 1 times lambda minus 2, this was equal to 0, and these were all to the power 1, okay? Which means that the lambda will be a single root. This is one important concept. Another concept is the geometric multiplicity. Which this geometric multiplicity, we can denote this one as Gn. Geometric multiplicity is defined as the dimension of the null space. Okay, so let's assume for a moment a matrix which can be 3 by 3. Okay, a matrix which is 3 by 3 we expect from here to have a polynomial of the third order in lambda, which means that we are looking for 3 different values for lambda. But the polynomial, let's assume for a moment that the polynomial can look like this. Let's say lambda minus 2 all squared times lambda minus 1. To the power 1, this is 0. So then what can happen in this case is the following. What is the algebraic multiplicity of 1? So we can say that an algebraic multiplicity of lambda equal to 1 is equal to 1. Okay? Then the algebraic multiplicity of lambda equal to 2 is equal to 2. Why? Because this appears, I mean, this is the power that we observe. So we're just going over this one, looking at a couple of examples. But what could happen is that sometimes, for a specific eigenvalue, the dimension of the null space, because let's not forget, we try to find the solutions of matrices that are going to look like this. And this is times x, this is equal to 0, and it could be that the null space here can have a dimension of 2. The null space can have a dimension of 2 only if the matrix is 3 by 3 and larger. We cannot have a null space equal to 2 if the initial matrix is 2 by 2, right? So assume that if the null space is equal to 2, then we can say that the eigenspace has a dimension of 2. So let me write here ordinality, which is the dimension of the null space of A minus delta I. This can be equal to 2. Okay. Why? Because when we try to find the solution of the null space, we can have 2 free variables. And where do we get? So if the null is equal to 2, that means that we have 2 free variables. And if we have 2 free variables, we should have at least one row which has a leading 1, right? So most probably plus, which means that plus the rank, and the rank can be equal to 1. The rank can be equal to 1, it can be equal to 2. Okay, then if this is the case, if you have 2 free variables because the nullity plus 1, this means that the matrix is 3 by 3. A is 3 by 3, right? So if we have the nullity is equal to 2, which means that we have 2 free variables, plus the rank, which can be 2, then we have a matrix which is 4 by 4. So how does a matrix 4 by 4, how would it look like? It's going to look like this. 1, 0, minus 1, whatever it is. So you should have a leading 1, then you should have another leading 1, okay? And then this is all, because this is rank 2, 0, 0, 0. So we're going to have, or let this be A and B, whatever. So these two will be the free variables. That's why the dimension will be of the nullity 2. And rank is equal to 2. Why? Because we have 2 leading 1s. So this would be a 4 by 4 matrix, assuming for some specific cases when the nullity can be equal to 2. And now we have also another important statement which we have to make, which is the following. Which is also a theorem, which states that a matrix n by n, okay, and it should be a square matrix, right, is diagonalizable a matrix n by n is diagonalizable let's say, if we can determine n eigenvectors. So if we can find n eigenvectors, then we say that the matrix n by n is diagonalizable. This is one important theorem. Another important theorem is the following. Any two distinct eigenvalues have linearly independent eigenvectors. Okay, this is also very important because in this case, what we can observe is that, for example, we have in the examples we solved in the previous session, we noticed that we had different eigenvalues and the eigenvectors, they were linearly independent. Also in here, if we have a situation where lambda equal to 1 is one eigenvalue and lambda 2 is another eigenvalue, that means that the corresponding eigenvectors will be linearly independent. Okay. So in this case, what we can say is that if we have a matrix which is 4 by 4, okay, and if we find 4 different eigenvalues, I'm just saying, so like -1, 2, 3, 7. Is this matrix diagonalizable? We say yes. This is going to be diagonalizable because since they are distinct from each other, that means that the characteristic equation is going to look like this: lambda plus 1 times lambda minus 2 times lambda minus 3 times lambda minus 7. This is equal to 0. All of them are distinct. The algebraic multiplicity apparently for each one of them is 1. But since they are distinct from each other, that means that we can come up with 4 different eigenvectors, all independent. That means that we have 4 eigenvectors for per matrice scatter mercato, which is 4 by 4. Then this means that this will be diagonalizable. So given these examples, then we say that A 4 by 4 is diagonalizable. So now the biggest question now is the following: if we have any matrix A, is it always diagonalizable? Because we can also have square matrices which cannot be diagonalized, and the lack of being diagonalizable or not is mainly in the fact that we cannot find 3 linearly independent eigenvectors. Okay. Let's see.
Professor, may I ask you one question? Maybe it's a bit.
Yes.
What can we call eigenvector?
Say it again.
What can we call eigenvector? What is eigenvector in theory?
In theory, the eigenvector is the solution. Are the vectors which are in the null space of this A minus lambda r. Okay. The null space of this vector is called an eigenvector. This is one way to answer, okay? And you already, so you might remember that I mentioned this a few times. Another way to define the eigenvector is the vector which the matrix does not rotate, right? So this is it. Did I answer your question?
Yes, thank you.
Okay, now, asking such a question, it looks like a very little bit incorrect, but please do ask these types of questions, because I'll try to make it clear, also we'll try to make it a little more intuitive, and that has been my objective since the beginning, okay? So what is an eigenvector? Well, an eigenvector, it will be the null space of this, okay? Which means that we first have to identify the eigenvalues, and then we have to identify a new basis, whose basis can be described as a function of the eigenvectors, whichever way they rotate in space. Okay. So this is the null space, and let's not forget that for each eigenvalue we have a different eigenspace. So, and let's have a look at an example. Let's assume we have a matrix A, which is 3, 0, 1, minus 1, 2 minus 1, 1, 0, 3. So what I can try to remind you is that what you can do, you can use a couple of comments. E, A, and the groups of P. So you can take a note for these two comments, which you can use in software, which can be called, you can either use Octave or MATLAB. And if you enter the matrix A, and you can find a characteristic polynomial using a simple command like poly, and then the eigenvalues, the lambda, will be the roots of this polynomial. So you can try this, and we will demonstrate this later in using the computer. But now, let's assume that this is the matrix A, and the question is, A diagonalizable. This is the big question. Is it diagonalizable? So then what we do is that we immediately write down the A minus lambda I, which is going to be equal to 3 minus lambda minus 1, 1, 0, 2 minus lambda, 0. So 1 minus 1, 3 minus lambda. Okay? So this is the matrix, and then we have to write down the determinant of this matrix, which should be equal to 0. So let's expand this this matrix along the first column because we have a 0 here. Then what we get is the following: we get 3 minus lambda times 2 minus lambda times 3 minus lambda plus 1 times 1 times 0 minus lambda minus 2. Right? This is equal to 0. So in this case, let's try to see what we obtain. So one thing that we can do is that we can, this is lambda minus 2, so we can write this one lambda minus 2, and here lambda minus 3, okay, and try to solve this whole polynomial.
Is it easier to expand the second row?
Say it again, how can we expand it?
For the second row.
Oh yeah, that's perfect. That's better. You are right. So if you do it, yes, we missed this one.
Make it easier.
Plus minus plus, this is 2 minus lambda, that is correct. Multiplying 3 minus lambda times 3 minus lambda. Now, this is, let's try this one, lambda minus 3 squared, because you put a minus 1 to both, no, oh yeah. And this is minus 1, probably, what is this? Is this correct? 2 minus lambda times minus 1. Yeah, this is true. So this is what we can do. And then here we have lambda squared minus 6 lambda plus 9 minus 1 plus 8. Let's multiply this lambda minus 2 because we multiply by minus 1 from both sides. And this term, this is lambda, lambda, this is minus 4, minus 2. So if we multiply minus 4 with minus 2, we get 8. So it looks like here we have lambda minus 2 squared, that's lambda minus 4, this is equal to 0. So it looks like we found the roots, and the algebraic multiplicity of the lambda equal to 2 is equal to 2. And the algebraic multiplicity of lambda...
Sorry, Professor.
Yes.
The first term, lambda minus 2.
Yes.
Was that 2 minus lambda at first?
Yeah, but I multiplied by minus 1 to both sides of the equation. I have 0 here, right?
I didn't see the minus 1 at the second.
Yeah, actually, I just mentioned it verbally. That is correct.
Professor, can I ask you something? How did you obtain the 2 minus lambda?
Say it again.
E perfectova că ecuațiunea 2 minus lambda, lambda minus stringator.
Well, this one is equal to 0, right? So we can multiply both sides of the equation by minus 1. We are not going to change anything fundamental.
I understood, but how did we get that?
Which one, the minus 1?
No, the whole equation.
Okay, yeah, this whole equation, the way to find this one is that we try to find the determinant of this matrix by expanding along the second row, okay? Because we know that always the determinant is equal to what? So if this is the second row, the determinant, it can be written as 0 times the determinant of -1, 1, -1, 3, minus lambda. Okay?
Understood. You have used determinant. I know how to find determinant. Okay. Okay.
So we are good?
Yes, understood.
Okay, thanks. So, but then this would be something like +2 minus lambda times a little matrix. Then we have the 0, which will multiply. Okay, so if we are good at this part, I can, okay, can erase this one. And then.
Why did we write lambda minus 3?
Say it again.
Why did we write lambda minus 3? I don't understand it.
Because we have this 3 minus lambda times 3 minus lambda. We can multiply here by -1 and here by -1, which means that I multiply by 1, right? So if I multiply by -1 twice, this is 1. So this becomes lambda minus 3 times lambda minus 3, okay?
Okay.
So we could do it. It's okay. So that's why we could transform it like that. But finally, we see that in this polynomial, in the third order of the unknown value lambda, this is what we obtain. This is the algebraic multiplicity and so on. Now, the question is, let's try to search whether it is diagonalizable, which is the same way to ask if we have 3 eigenvectors or not. Okay. So let's try to find what eigenvectors we have for lambda equal to 2. If lambda is equal to 2, we have to write down this equation A minus 2i. Okay. I is the identity matrix. A is the original matrix. And we need to find the null space of this matrix. So what is A minus 2i? A minus 2i, we obtain that we have here 3 minus 2, this is 1, minus 1, 1. Can you see this, how we got this? Then we have 0, 2, 0. If you subtract minus 2, this becomes 0, 0, 0. And then we have 1 minus 1, 1, 1, minus 1, and 1. Or I can write it like this. This is 3 minus 2, this is 2 minus 2, and this is 3 minus 2 again. Maybe it's better if I write it like this. This is equal to 1 minus 1, 1, 0, 0, 0, and 0, sorry, this is 1 minus 1, 1. So we want to find the null space of this matrix. The null space of this matrix, we can do a further elimination. If we do row 3 minus row 1, we get, this is not equal, this is equivalent, right? Because they cannot be equal. And this information, we don't need this for the moment. So this is equal to 1 minus 1, 0, 0, 0, 0, 0, 0, 0. How many leading ones do we have here? We have only one leading one, so we have 2 free variables. So if we're looking for solutions that look like this A, B, C, and this is all equal to 0, then we have 2 free variables. So here we have B is equal to a free variable S, and C is equal to another free variable P. And S is any real number, which means that S is from minus infinity to plus infinity, including the 0. Also, T is a real number, which is anything from minus infinity to plus infinity, including the 0. And then, what are the equations that we get from here? The first equation, sorry, there is a mistake, the 0 is 1. Right? Yes, it's 1. So, the first equation that we obtain is the following. We have A minus B plus C, this is 0. The second equation, B is equal to S, and the third equation, C is equal to T. These are the 3 equations. Then, let's substitute for B and C the free variables S and T. Okay? And here we obtain that A is equal to B minus C, which is S minus T. B is equal to S, and C is equal to T. So this set of equations, they are both equivalent with respect to each other, and then, but it looks, by the way, it looks immediately that since we have two free variables, the nullity of the eigenspace of lambda equal to 2 is equal to 2. So I'm going to write this also on the board. We have here ABC. This is equal to S plus P. So the S, this is 1, 1, 0, because these are the coefficients of S. And then we have minus 1, 0, 1, minus 1, 0, 1. So here we have two different eigenvectors for lambda 2. So then at this stage, so we find that the matrix P, if we will be able to find one, is composed of 1, 1, 0, 1, 1, 0, minus 1, 0, 1, minus 1, 0, 1. And we're looking for the third one yet. But at this stage, we can say that the dimension, or dim, of the eigenspace of lambda equal to 2, this is 2, right? This is equal to 2. Which means that we have two eigenvectors. Two eigenvectors corresponding to lambda equal to 2. So this is important. Then the next step is we have to identify the other eigenvalue which might correspond to this lambda equal to 4. So we do the same thing. We say 4 lambda equal to 4. We have, let's write the equation A minus 4I. This is equal to, we have 3 minus 4 is minus 1. Minus 1, 1. Then we have 0 minus 2, 0, because it's 2 minus 4. 1 minus 1 minus 1. Then let's try to obtain the reduced row echelon form of this expression. So the reduced row echelon form here. Let's multiply the first one by minus 1. We get here 1, 1, minus 1. And then let's add the first and the third. So the second one we can divide by minus 2. This becomes 0, 1, 0. If we add the first one and the third one, here we get 0, minus 2, 0. Then here we have a leading one, here we have a leading one. Then the next reduced row echelon form, it can be described as this 1, 0, minus 1, 0, 1, 0, 0, 0, 1. This is a 3 by 3 matrix, and we have only one free variable. So the free variable, it will state that C is equal to S. Okay? And the set of useful equations, we can write them somewhere here on the board. Let me take this away, because this was simply. So we have A minus C is equal to 0. Then we have B is equal to 0, okay? So B is clearly equal to 0. And C is equal to S. Then we say that the vector ABC, this is equal to a variable S, 1, 1, 0. So here we have 1, 1, no, 1, 0, 1, sorry. This is 1, 0, 1. Okay, so apparently, the initial question, whether A is diagonalizable or not, we started to analyze it. We found the characteristic polynomial. The characteristic polynomial in order 3 has two solutions. One is lambda 2 with algebraic multiplicity equal to 2, and one eigenvalue which is equal to 4 with algebraic multiplicity equal to 1. Then we try to, but we observe that the geometric multiplicity of lambda 2, so GM of lambda equal to 2, this is equal to 2, and the geometric multiplicity of lambda equal to 4, this is equal to 1. So then, if the geometric multiplicity is equal to 2, that means that we can get 2 eigenvectors from here, plus 1 here, 3. So the moment we have 3, we say, is A diagonalizable? Then we say yes. Okay, any question?
Professor, I wasn't following. The 3, what does it mean?
Say it again.
3 شيطانين në fund, çfarë do të thotë?
So, if we can find 3 different eigenvectors for a 3 by 3 matrix, that means that we can diagonalize them. Okay?
Okay.
Okay, any other question? If you have no more questions, we can end this session.